All right. Hi everyone. Thank you for coming today. So today our speaker is Nando Fioretto. So Nando is right now an assistant professor in computer science. He's at the University of Virginia. Before this, he was actually at Syracuse, and before this he was one of us at Georgia Tech in ISYN. He was doing his postdoc here. And Nando does kind of like a lot of work on like trustworthy and responsible AI, on AI for science and engineering. And today he's going to tell us a bit more about his work on responsible AI, and he's going to tell us about the unintended effects of privacy in decision and learning tasks. And so, yeah, take it away, Nando. All yours.
Thanks, Chiba, for the kind of introduction. So I'm really excited to be here talking about this topic. And firstly, really my recognition goes to the amazing students that have collaborated with me along a few of the projects that you're going to see through the slides. KU Georgia Tech and me and Kwang, that are two of my students here. So let's get started with some context. Optimization and learning systems are now becoming more and more instrumental for making many decisions, especially in policy operations that are involving individuals. And so this is including in assisting, for instance, in legal decision, determination related to whether individuals will qualify for benefits such as loans, as well as assigning resources to entitled individuals. So those are just a few examples, but often this success of this technology is associated to the presence of rich data sets that contains personal identifiable information. And the use of such data sets combined with the adoptions of black box algorithms has also sparked concerns about how the systems are operating. And two key concerns relate to the how much information the systems leak about the individuals was data is used as input, and how to discriminate or how do they handle discrimination. And this is a really pressing issue. In fact, we have seen just a few days ago, this actually, it's an older slide here, but we have seen just a few days ago another sign from the White House with the advancement of trustworthy AI commitment that we'll now have. So this is a part of a larger conversation. And so within privacy, differential privacy has become the paradigm of choice for protecting data. We have also seen deployments growing at a fast rate. This is including the products released within the 2020 census, as well as Google, Facebook, Apple, Uber. They all have their own set of releases. And so differential privacy is really appealing because it bounds the risk of disclosing sensitive information in individuals that are participating in a computation. But the process that it is used to render the data or the model privacy preserving inevitably might affect some important properties in the outputs. And in particular, it has been recently observed that systems that satisfy this notion of differential privacy, they might induce bias or unfair outcomes for different groups of individuals. And so those results can obviously have significant societal and economic impacts on those individuals. And to give you an example, so this is the Title I of the Elementary and Secondary Act. This is one of the largest US program offering educational assistance to disadvantaged children. What we're doing here is we're allocating a budget to school districts, and this federal allotment is divided among qualifying school districts based on a proportional count of the number of children in that districts whose family fall below poverty line or receive some form of financial aid, and some weight factor which represents some student expenditure in the state. And so this allotment here TUS is distributed and is formalized with the formula that you're seeing on the bottom left. And the figure here on the right illustrates the disparity of the errors that are arising when we're using privacy-preserving data in the allocation problem. So the yellow part here is rendered privacy-preserving. And so those errors are expressed in form of US dollars misallocation on the right axis, and on the x-axis you have the school districts sorted by side in the state of New York. And so here, what you can see is that some school district may receive for this choice of privacy budgets up to $42,000 less than were warranted, so resulting in large fairness issues. Other examples are arising in the context of learning systems, as were observed by Bhattacharya. Firstly, would measure the accuracy of differentially private classifications in a gender and age classification task, as well as on a sentiment analysis task. And essentially what they notice is that the groups that are analyzed here, they have either lighter skin tones or darker skin tones for the gender and age classification task, or they speak standard American English versus African American English. And so the key outcome of this study is that differential privacy affects the accuracy of the minority group more than it does on the majority subgroup. And so this can result in significant effects in society. So classification error may penalize grouping determinations such as criminal assessment, hiring, landing. Biased decisions can result in disparity in the allocation of funds, benefits, therapeutics. And so we are interested in understanding why such reasons are arising. They are becoming more and more apparent, but yet there is still some need of understanding why such issues are arising. And so this is a bit the outline of the talk. We're gonna look, we're gonna take those observations and look at them in a couple of settings. So in the first setting on the top, you see, I'm not sure if you see my pointer, you see a data set which contains sensitive information. Then we have a mechanism that produces a privacy-preserving data set. And then where this data set is not going to live in a vacuum, you're going to use it for some tasks, especially we're looking at some allocation tasks, and we want to understand what are the impacts on the fairness impact on the final decisions. And in the second setting, we're going to look at a learning task. And so here, we're not going to use a privacy-preserving data, but the model will be rendered privacy-preserving. And once again, we want to look at the fairness impact on the outcomes. And so, so this is the agenda. So let's get started with some preliminary, and we're going to take a closer look at stats publishing from with a census perspective in mind. So in the US, every 10 years, the census surveys the American population. The goal here is to enumerate the US population. And so this is not just a statistical sample. It connects a lot of information about the individuals, and it's a rather a unique task. And it's a very, very important task because the data collected by the census is used to determine the seats that each state has in the House of Representatives. And it is also used to distribute the $1.5 trillion budget. Particularly, it is used to distribute the $665 billion allocated to over 100 economic security programs. And those security programs here are really, really important because they every year they are lifting millions of people above the poverty line. For instance, in 2019, those programs were able to lift over 6 million children over the poverty lines. So getting accurate count, it's really important, but also, and so Congress mandates data collection. But on the other hand, the census is also required by Congress to retain confidentiality of the data due to Title 14. And so to deal with such type of regulations, the census has adopted a variety of disclosing avoidance techniques since its early day. They include data suppression, shuffling, anonymization. But recent observation have also let us notice that the attacks have evolved during the years. And for instance, there was this very important attack carried out by folks at the census on their own 2010 data release, which was anonymized with the same techniques used since the early 70s. And so essentially they carried a linkage attack, and they were able to reconstruct large parts of this anonymized information. They were able to reconstruct correctly all inhabited blocks. They were able to reconstruct about a half of the populations when you're considering block size age, race, ethnicity. And if you're allowing a slack of 1 year, this number bumps up to 71% of the population. And they were able to re-identify, so this includes having first and last name in the data of over 1/3 of the American population. And so essentially they asked the question, what can we do to protect this information? And as we all know, they took this really, really brave action of using differential privacy, and we're all glad about it. And so just in a nutshell, here we're looking at a randomized algorithm that satisfy this notion. So in a nutshell, it's telling us that if we have two instances of a word in which we have a dataset D1 in which you are not participating into, and another word in which you have a copy of this dataset, except that you also have an additional entry in which you are participating into, and we call this D2, then an algorithm run on D1 and D2, and these two instances of a word, should effectively have almost identical outcomes, right? And so we really want to bound the ratio of the probability of generating any outcomes. And so the intuition here is that an adversary should not be able to distinguish between the two data sets that the first by the participation of an individual just because they have observed the output. So the P satisfies several appealing properties, including immunity to linkage attacks, so the attacks that the census carried on its over 2010 data release, as well as composability, so we can compose primitives to create algorithms that are more complex and still being able to reason about the overall privacy loss, and post-processing immunity, which essentially tell us that DP guarantees are immune to any type of post-processing step, which is data independent. And so there's, as I think all of us are aware, there's various algorithms that and primitives that we can that allow us to define such type of differentially private property. But for the purpose of this talk here, we're just going to focus. I mean, it's just going to be important to know that we're going to add some noise somewhere in this process of either releasing the data or releasing the model. And particularly, we're interested in adding some unbiased noise. So let's now delve into the heart of the problem. So let's see where fairness impacts might arise in a DP decision-making task. So here, the focus is to study. Oh, and by the way, I haven't said this earlier, but feel free to interrupt me and ask question if there is any question during the talk. So the focus of the study here is to study the effect of a differentially private data release mechanism, M, here. And so we are going to generate a new data set, X tilde, which is the privacy counterpart of data set X. This satisfies this notion of differential privacy. And then we want to apply this X tilde into a decision task. So for instance, this problem, this decision task P might represent an allocation problem, the amount of money that we want to allot to a school district, or maybe a particular rule, such as whether some election ballots should be translated in a minority language of interest. And now, because random noise is added to the original dataset X, then the output P of X tilde here will incur some error. And so one of the goals here is to characterize the disparity or the disparate impact of this errors among the problem entities. And so to quantify these errors, we're going to focus on the problem bias, which is a measure of the distance between the expected privacy-preserving allocation and the allocation obtained using the ground truth data. And then we can say that the process is alpha pair whenever this bias is the max differences across biases across any entry is bounded. Okay, so let's take a look again at the problem that I was introducing very earlier in my slide. So what I was saying here is that there is this unfairness effect, which is arising due to the addition of noise. And now all what I wanted to notice here is that all what we had done was in that process to measure this bias was just introducing unbiased noise. Okay, so there is no other action here. And so the first question that came to my mind when we have this observation is then where does this bias come from, and why we have such type of effect. And so the first result that I wanted to discuss is that to understand why this bias arises, we looked at the problem that we were analyzing, and essentially realized that it is really the shape of the problem, the shape of the decision problem, that characterizes the unfairness of the outcome. And this holds true even when the decision, even when the noise induced by the DP mechanism is unbiased. And you can see why, because this term, this bias term here can be approximated by an expression which involves the local curvature, right, at a given entity, and the variance of the noisy inputs. And thus, fairness can be bounded whenever the local curvature is constant across the entities, because also the variance is constant and bounded. But then you're inevitably going to have entities which have different local curvatures across the process. And so an important corollary here is that fairness cannot achieved for any program that is a nonlinear function, perfect fairness, right, cannot be achieved for any program that is a nonlinear function. And this is in the case for any type of allocation or decision problem that we have studied and we generally see. And so if this is not enough, so I want to look at a different problem, and then we'll try to reconcile this this notion here. So this problem here is the problem, or is called a coverage of determining which jurisdiction in which jurisdiction we should translate materials such as voting registration, ballots, and instruction in a minority language. And so this is a coverage which is determined by the census every 5 years. There were about 22 million people, 22 million voting age citizens, which were potentially impacted by such type of coverage here. And essentially what we're doing here is using information about the individuals to determine whether such jurisdiction should adopt translation or not. And the information about the individuals that we're using includes the number of individuals that are speaking a minority language of interest, those that have low-grade education, as well as those that have limited English proficiency. And so the figure on the bottom right here shows the decisions errors that we're doing for the Hispanic language when we're sorting the on the x-axis based on the number of people speaking the minority language. And so the errors here are in the true positives, which are particularly important because they imply that misclassification potentially implies disenfranchising a group of individuals. And so what is interesting here is that this figure shows a significant disparities in the decision errors as and it correlates this strongly with the distance to a threshold. And this threshold here is this 10 to the 4th. And so I think that this is a really important observation, because what it says to us is that just because you're an individual that lives in a jurisdiction which has certain type of feature, in this case it has a minority population satisfying those properties, so being close to this arbitrary set threshold, then you might potentially being more affected, right? And so you have more potential of being disenfranchised. And so we wanted to also understand why those type of disparity were arising. And now we're in a context in which those decision rules are much more sophisticated. So we don't have, in the previous setting, we have a function which we could approximate with it was a continuous function, it was twice differentiable. But in this case here, this is a highly discontinuous function. And so the analysis that we've done earlier does not apply here, but we could look at segment of this function here and try to understand what happens there. And so we looked at those ratio functions. And so here, what I want to focus on is this illustration. So in this illustration on the right, we have 3 counties, and we're showing the absolute bias. So this is the error that we're making for estimating the ratios, right, when those ratios are privacy preserving. And so the blue dots are the real values associated with the ratios, and the red crosses instead is the expected value. So here it's really the error. And so what you would like to have is this red cross to be as close as possible to the blue dot. And here, this is arising for some so for some counties, but for other counties, you notice that you have much higher bias. And so we were asking why. And at the beginning, when we were looking at this data, so you notice that all those ratios are all close to 0.05. So there is not really a big difference for us to differentiate them. So when we were looking at those numbers at the beginning, when my students was communicating this to me, we were really puzzled. But then a further look at the data show that those ratios don't born equally. So numerators and denominators are highly different, and thus inducing noise to, say, smaller numerator might have much larger effect than that of inducing noise to a larger value. And so this is important because essentially it tells us that we needed to look at data at another granularity, right, to understand what was happening there. Another aspect that arises in this context here is, so we try to look at compositional results. So composition is a very important property of differential privacy. And we ask whether some form of composition still holds when analyzing this disparate impacts. And so here in the figure on the right, I'm showing the error, which is due those particular thresholding functions. So the pink component and the blue components associated with those dots over here on the right hand side. And then in green, you have the error associated with the logical combination and logical combinations of those two thresholding functions. And so you notice here that the green dot, it's always above the pink and the blue dot. And in fact, here we show that this error here, it's always upper bounded. So if you have two fair mechanisms, then the logical combination of them is always lower bounded by the max of the alpha fairness of the individual propositions. And so this leads me to discuss the first key result of this study, that using differential private to generate private inputs for decision problems will necessarily introduce some fairness issues, despite the noise being unbiased. But now that we start understanding why this is happening, then we can start thinking in how to mitigate such type of effects. And so one observation here is that those issues that we're observing are data-driven, are not data-driven, but are actually problem-driven. And so an interesting corollary of the previous result is that if the program that we're using, it's a linear function or the input, then a mechanism is going to be fair, is going to be perfectly fair with respect to this program. And so a solution that we developed for the first program was that of linearizing, right, the expression that we're using for the allotment. Now, there's many linearization techniques that we can exploit from mathematical programming, but the idea that, simple idea that we try here was simply take the, well, so if you notice this ratio formula here, it's a nonlinear expression, but if the denominator were a constant, then this now it becomes a linear expression with respect to the inputs. And so we release a noisy version, right, of the denominator at an additional cost, at an additional privacy cost, and thus this can become then now just a linear expression. And so here, the first plot, we're showing how the fairness, the unfairness decreases. So the pink model is the original model. So this is the allocation that it's done, the bias of the allocation resulting in the original model. And then obviously after linearizing the problem, this unfairness drops to 0. But then it's important also to notice the relation of the errors that we're inducing when we're using the original program in pink and the new program, the linearized version of the program in green. So we are not really losing much in terms of errors. The errors are really comparable. We look at also the in the second problem, and once again, this is a much more difficult scenario, but we resorted to this linearization trick again. So here what we did was, if you think about this, these characteristics of the populations that we have, so we have several characteristics, and so we treat them as features, and then we fit a linear regressor or a linear model to approximate them. So we try with a linear regression and with support vector machine, and then we take the weights of those models, of this linear model, to approximate the final decisions that we're going to induce. And so here we can have much better fairness violations. So the fairness, when we are looking at different segments of the population, the fairness reduces from the pink bars here to the green or the orange bars, so reduces significantly. And so this is a really really interesting step, because now we're able to commit to decision rules that somehow are cognizant of such type of errors that we might make. So I want to now to discuss a second aspect that arises in this data release pipeline. So far, essentially, we said, well, you take your input, you add noise, you're releasing it, and you're using it. But actually, that's not typically what's happening. So what is happening in the data release pipeline is that before releasing your privacy-preserving data, your data might undergo another step, which is a post-processing step. So why? When you're releasing the data, that is just a noisy version of the original data, this data might violate some problem characteristics. So for example, in census data, you have hierarchical properties which needs to be satisfied. So counts at the level, say, of a state needs to be consistent with the sum of the counts at the level of the underlying counties, and so on. So you have those hierarchical properties that, through the addition of noise at each count and each level, will be destroyed with very high probability. Additionally, typically here we're releasing counts. Those counts are non-negative numbers, so the addition of noise will create, with high probability, negative numbers, especially when those counts are small. And so what people do is post-process those counts in order to satisfy such type of constraints. And so you typically see this as a projection step. So and that's onto the feasible space. And so here, for instance, we're considering space of linear constraints. And so something that I want to focus here is now this illustration. So in the first image, in the first picture, we're showing a set of counts, which are just a frequency count for a randomly sampled set of individuals. The second subplot shows the residual errors after applying a Laplace noise on top of those counts. So you see that this errors is equal, and so the residual error is equal across all counts. Then we're applying just a projection onto the non-negative ortant, and now again you notice the residual error. And then finally we're applying a more sophisticated projection where we're also satisfying hierarchical constraints. So all those projections, they guarantee the same level of privacy. So the first thing that you can notice is that there is an error reduction, and this is not really surprising. There's many people that have studied such type of error reductions here in post-processing steps, but also notice that the error decreases differently, right, in different segments of the populations. And so here we asked why, and so I'll spare you the suspense. This is due to the presence of these non-negativity constraints. In fact, we show that when we have more general constraint spaces, more general linear constraint spaces, if you're removing the non-negativity constraints, then you can still obtain an unbiased estimator of this projector here. And so here, we show that the results here relies on showing that there is an L1 ball of certain radius, which is centered at the point in which you're inducing noise, which is a feasible subspace of the projection where there is no bias. And so we can upper bound the complement of this ball here. And so, for instance, what you can try to do here is, in this illustration on the bottom, we take two counties and we show in blue the residual errors that we're making when we're using Laplace noise, and then in red, the post-process residual error. So you see that there is this high bias around 0, but then we start shifting every single count by 5, 15, and so on, and then this bias progressively disappears. And this is because this radius here is getting larger and larger. And so this has a really important practical implication, because essentially tell us that post-processing reduces the variance of noise differently in different regions. And this effectively, especially affects a region with many subregions. And so, for instance, we have analyzed how such type of variance differs in Arizona, which has 2.37 million people and 15 counties, versus Texas with 8.9 million people and 254 counties. And so here there is about 6.5 differences in percent in biases, which is, can make huge changes in allocations of billions of dollars. And so the second important message here is that although post-processing reduces errors, we should be cognizant of its applications when we are using such type of technology for allocating when we are making important determinations. Next, I want to bring some of those results into the context of machine learning. So here, the context is slightly different. So we still have a sensitive data set, but we're not releasing this data set. We're using it as it is, and then we're modifying the weights of this learning mechanism here, and we want to study the impact, the fairness impact. And so we do that by doing the classical empirical risk minimization, and our fairness notion focuses on the definition of the excess risk, which looks at the difference between the private and non-private risk functions here, where the expectation here is defined over the randomness of the private mechanism. And so here, so basically this expression is how much loss are we losing, right, because of the private process. And so what we want to do is to look at this loss across different groups, right? And we say that a mechanism is achieves a certain fairness level whenever we can bound these differences in loss due to privacy across different groups. And so we looked at several mechanisms, but here I'm going to focus on the DPSGD, which is the de facto standard DP algorithm adopted in privacy-preserving ML. So essentially, it's an adaptation of stochastic gradient descent. So stochastic gradient descent works as follows. You take a mini batch of data, you do a forward pass, you get an estimate, y hat, of your label, you compare this estimate with respect to the ground truth label with a differentiable loss function, compute the gradients, and then update your weights in the opposite direction of the gradients. And in the DPSGD, we're doing all those steps, but also we're adding two key components. Firstly, we're clipping the gradients in an L2 ball of a given size C, and then we're adding noise from a certain distribution before propagating the signal back. And so what I'm going to show you is that those two characteristics of the DPSGD are both key components that affect or exacerbate the unfairness in this process. And so in this result here, I don't want you to parse the expression. This is just here to show that those two components are actually present in this evaluation. So we show that we connected the expected loss for a given group A with its excess risk, which in turn is used in our fairness analysis. And so this formula here essentially decomposes the expected loss that is used during private training with three components. The first is not affected by the private training. The second one relates the model parameters. The other two instead are relating the grading clipping and the noise addition component, and together they capture the notion of excess risk. And so if we examine those components, in isolation, this first component here has two subcomponents. The first involves the Hessians of the loss functions at a given group. This is here just to tell you that when we're looking at the effect of those Hessians here, of this part of the component of the excess risk, this is really negligible, so we're not gonna focus on it. The other part instead is the presence of those gradients, or the gradients flow. And informally, the gradients flow affect the excess risk of the individual groups. As we can show here, there is a very strong correlation between the gradient norms for each group. So those are the gradient norm of a given group at convergence, and the resulting excess risk, right? And so we can see that groups having larger gradients norm, they are also having larger excess risk. And so geometrically, this essentially can be explained by imagining that you have two groups that have two different updates. So one group has gradients that are smaller than another group. And so this group here on the left that are a smaller gradient, when we're clipping their gradient, they're going to lose less information with respect to this group here on the right. And so we can see this gradual decrease in unfairness when we're increasing the clipping bound, right? The second result is, why then this unfairness also arises due to the presence of noise. And so here we were able to show that there's a strong correlation between this Hessian term that arises in this component due to noise and the distance to the decision boundary. And so, in fact, I mean, informally, this is obvious because individuals that are close to the decision boundaries are they're going to have higher Hessians and they are less robust to the presence of noise, right? So their result may change more abruptly with respect to the presence of noise. Thus, intuitively, you can think at those individuals having much sharper Hessians than those that are farther away that can be better separated. But once again, now that we are able to get some understanding of why this unfairness arises, then we can start thinking on how to build mitigating solutions. And so here we try something simple. We build some proxy functions that use those gradients components, right? And those Hessians components, those were the factor characterizing affecting the excess risk due to clipping and noise addition. So we equalize their differences across groups and use those as a regularizer in our loss functions. And here, this is just an ablation study that shows you how the excess risk progress for a variety of privacy budgets when we deactivate, we don't have those components, and when instead we do have those components. And so you can see that there is a much smoother progression of excess risk, the reduction as well as reduction in fairness. All right, so in the last, I guess, few minutes, I'm just going to discuss a little bit of, what excites me and what is my group working on. So far, I've been extremely, pessimistic in my slide. Essentially, I've been saying, well, differential privacy induces unfairness, and thus we need to be really, really careful. But recently, I've been focusing on the reverse direction, or better, in a direction that is looking at the problem from a different angle. And this is this is so in a sense not focusing any longer on the negative impact, right, of privacy onto the decisions, but really focusing on the positive impact of DP onto the decisions. Why? So I believe this is important because if you remember, following the release of the 2010 demonstration by the census, they reported an analysis of errors and equity issues, and this has started creating a veil of skepticism, right, among data users. The skepticism even caused the filing of a lawsuit from the state of Alabama, which was fortunately ruled out. But essentially, the skepticism can cause other federal agencies to restrict data access and thus might impede some important studies. And so here we really seek to ask whether more traditional technologies or data suppression technology would create more inequity than releasing noisy DP statistics. And so we started looking at what happened when you compare this differential private statistics with respect to more traditional self-suppressions, for example, which are essentially, you can imagine them as fancy version of low-pass filters. And so here we notice we don't really have a way to compare those methods formally, but we try to do so by rendering those deterministic mechanisms stochastic, so adding the smallest amount possible of noise so that those mechanisms still preserve their essence, so they are close in errors with respect to the original mechanisms, but now at least we're able to derive some privacy bounds, and so that we can at least analyze, make a comparison with apple to apple. The first thing that you notice is that you get huge deltas from those mechanisms simply because of their nature. And you could clearly see this when you mount some reconstruction attacks. So you can see that it's really, really easy to reconstruct a large number of individuals when you're using such type of self-suppression mechanisms. But also, surprisingly, we noticed that in most of the cases that we study, the DP mechanisms tend to have better accuracy when we're looking at aggregated statistics, and tend to have better fairness issues, so better, smaller differences in accuracy across various groups than when we're comparing this with self-suppression mechanisms. I'm also interested in studying, I think that you could consider privacy as a, especially in the context of machine learning, right? You want to find an answer in a space of hypothesis, and when you're now using privacy on top of your mechanism, you can think at restricting the space of hypothesis across all those that satisfy this notion here. So I like to think at this context as a kind of constraint. So we started looking at other type of constraint that you might have within such type of hypothesis spaces. So particularly when you look at efficiency. So if you look at network pruning, which is a technique that removes low importance parameters in your neural network, so to reduce the size of the models, we looked at such type of techniques creates or exacerbates biases that might be present in the model and the data, and so we have an analysis on why such type of effects are arising. And recently, we also looked at another aspect. So in the models in which you might not be subject to choose, how do you call it? Okay, so in a service, apologies, in open services where you might not be able to select the hardware in which you can train your model, there is a really interesting aspect which arises. The hardware selection, which might just be due to the end user, might creates an implicit fairness issue. And so, for example, here we compared model trained on different hardwares, and we look at the differences in accuracy that exist when you're looking at the final model returned by those different hardwares that are just called by API with an AWS pipeline. And so we show that there are groups, minority groups here, they suffer much larger variance with respect to majority groups, and this variance here is exacerbated by the type of precision or the type of hardware, essentially, how the hardware can process different characteristics of the inputs. So to wrap up here, this study here was motivated by the use of the combinations of the use of rich data sets and black box algorithms. We show that several algorithms can have significant societal impacts, including allocation of funding, language assistance, and they can exhibit unfairness when applied to DP data release tasks. And so we look at two tasks. We look at in decision making, we characterize the conditions for which those problems have finite fairness violations. We're also able to study some guidelines to act on such decision problems so that we're able to mitigate such fairness issues. And in learning task, we studied a characterization for the reasons why differential privacy starts to disproportionately affect the accuracy of learning task. So all in all, I think this is a really, really exciting area of research. And I'm really excited because it requires cooperations of multiple areas. And I'm really looking forward to see where this will bring us. So thank you so much for your attention. And I'm happy to take questions if there's any.
Thank you, Nando. Yeah, we have about 7-8 minutes to take questions right now. So if anyone has any question, please let us know.
I have one question. Is the core issue here the fact that different groups have different sample sizes? Is that the reason that why we add differential privacy, then we get disparate impacts on these groups? Or in other words, if I had multiple groups of relatively similar sample, like size, would I still encounter this problem?
So that's a very good question. So the question is the correlation of the unfairness related exclusively to the differences in group sizes? And the answer is no, but a lot of it is. So like in learning tasks, so in the analysis that we have over there, the grading components are highly affected by the group size. So you can think that the process will follow the direction of the majority group, and so at convergence you might have converged for everybody, but actually when you're analyzing this gradients for different groups, then you find that because there are very different loss surfaces, then you actually have small gradients for the majority group, but larger gradients for a minority group. But this does not arise, for example, in many settings where we have the equally spread individuals. So, and the issue that we often observe there is the issue of separability. So you might have groups that are just more separable than others, just given their ability to correlate better, right, with the label. And even if you have equal size, groups, then you have those groups that are less separable, that are inevitably much closer to the decision boundary. And if you do a robustness analysis, right, then that will result in larger, fairness issues due to the presence of noise.
Got it. Thank you.
Thanks for the question.
Do we have any other question? I don't want to ask you a question because I already know your research. You talk all the time, but if anyone else has a question. All right, then I'm guessing if there is no question, we can probably call it a day. So